Welcome to the lecture of Flexible AC Transmission System. This lecture will be the continuation of our previous lecture, that is TSC TCR type of SVC. So we will see the VAR demand versus the power output characteristics of the TSC TCR type of the SVC. In this waveform, here this is the QC demand and this is the QL demand, that is reactive power demand of the capacitor, and this is the inductive reactive power demand. And along the y-axis we have the reactive power supply, that is capacitive power supply on downside, and inductive power supply, that are inductive power supply on the upward side of this y-axis. So when we put the capacitor C1 into the action, we will get this much of the stepwise the capacitive power output, and when we switch on the C2 capacitance, then we will get the second step output, that is our capacitive power output is increased towards this second step, and when we switch on the C3, then we will get this much power output. So our maximum capacitive power output will be till this point. Now this is the stepwise output, capacitive output which we get, and this stepwise output can be converted into the smooth output with the help of the smooth variation of the inductive VAR output. So inductive VAR output can be controlled with the help of alpha. So we will get this with the help of one inductive VAR output. So you can convert into the ramp or ultimately the smooth waveform, and to approximate the VAR demand, the net capacitive VAR surplus has to be compensated by the inductive VAR. So you can inject a little bit of inductive VAR to cancel this surplus VAR generated by this capacitance. So accordingly you can change the VAR. Ultimately you can make it also inductive VAR by switching only the TCR. So when only TCR is switched here, so you will get this much of reactive power output. This is the dotted line which shows the delay in order to provide the enough overlap between the switching in and switching out. So what we can conclude from this, the approximate VAR demand with the net capacitive VAR surplus the relatively small inductive VAR output of the TCR, that is QL, it is used to cancel the surplus reactive VAR. Obviously it is a small amount of reactive VAR, so the rating of reactor is kept relatively small, that is 1 by n times of the maximum capacitive VAR. Here if 3 units are used, then we will get this much of maximum capacitive VAR. So this maximum capacitive VAR divided by number of units, number of capacitor units, will get the rating of one capacitor unit. So the rating of one capacitor unit should be equal to rating of this one inductor unit, and this inductor unit rating should be quite larger than this capacitor unit rating to ensure the there should be something phase difference or time difference between the switching in and switching out. Now we will see the control scheme for the TSC TCR type of SVC and see that how it can be controlled. First of all, we require to know that what can be the maximum VAR requirement of the particular site. Suppose if we require the 8 MVAR, and from there we have to design the size of the modality, so what should be one branch capacity of the compensation. So let us see. With the all constraint, the thyristor rating transients has to be put into the operation, and we have to find out that suppose 1 MVAR will be the suitable. So it can compensate the maximum capacity of up to 8 MVAR by switching the 8 such TSCs, and you should have one TCR operating around slightly greater than 1 MVAR, that is the rating of one capacitance. So suppose TCR operating around the 1.2 MVAR, so that there will be a little overlapping and you can be able to compensate in the right manner, and you can manage with the combination of the TSC and TCR. So the precision will be set by the TCR. So TSC will give you the stepwise compensation, capacity compensation, and it will be slightly greater than your demand, and that slight difference will be compensated by the TCR. So the control scheme first determines the number of TSC branches needed to be switched in order to approximate the required capacity output current and compute the amplitude of the inductive current needed to cancel the surplus capacitive current. So for our example of 8 MVAR, we require 5. If we require the 5.3 MVAR, then it will come down to the number n. So that number will be equal to 6. So that we can get the 1 MVAR into 6 is equal to 6 MVAR, and the 0.7 MVAR difference that we have to inject with the help of TCR. So it will compensate that difference, and so that it will compute the delay angle for it. So delay angle can be computed online by the processors, or there may be have some program, so that the every degree of alpha it can have a particular current value. Secondly, it controls the switching of the TSC branches in the transient free manner. That is very important. While inserting the capacitor, you have to do the zero voltage switching, so that the circulating current should not flow through the circuit, as we discussed previously, to ensure that the supply voltage and the capacitor voltage should be same. So if there is a voltage difference between supply voltage and capacitor voltage, then circulating current will flow, and it varies the current in the TCR by 5 angle delay control. So these are the 3 functions of the control scheme. Now we will see the detailed control scheme of the TSC TCR type of SVC. So the first function is simple. Here you require the input current reference IQ reference, that is requested output current. The output current we required here, it is divided by the current IC. So number of capacitance we are connecting here, number of capacitance branches, and to calculate the IC we will divide, to calculate the number of units we will divide the current IC, current rating of the capacitor, to the IQ reference, and the result will be rounded to the next higher integer, and that will give the number of capacitor banks needed, that is it may be from 1 to number n. So we have the n such capacitance numbers, and ultimately we have one TCR branch. Then you will compute the required capacitor and reactor current from this. So required capacitor current is calculated, this IC, and then required IL of alpha we can calculate as IL of alpha is equal to summation of this IC currents, capacitance current, minus the total IQ reference current. So we will get IL of alpha equal to summation of ICN minus IQ reference, and TCR firing angle will be decided accordingly, and we will get the triggering pulse to the thyristor of the TCR. So for our example of 8 MVAR, if we require 5.3 MVAR, it will come down to the number n, so that it will be 6. So it will switch on the 6 such branches, and from that we will get the 6 MVAR output, and the fractional part, that is 0.7 MVAR, that will be compensated by the TCR, and for that MVAR it calculates the reactor current, and for that reactor current from any program, and for that reactive current it will calculate the firing angle alpha, and so the firing angle control will be there. Now we will see the basic control logic for the second function, that is the switching of the TSC branches in the transient flow manner. So this follows the two simple rules for the transient phase switching, that is either the switch of the capacitor bank when the voltage across the thyristor wall becomes 0, or we can when the thyristor voltage may be minimum. So when the thyristor voltage may be 0, so this condition arises when the capacitor residual voltage is less than the peak AC voltage. So suppose if peak voltage is higher and this capacitor residual voltage is lower than this peak voltage, peak supply voltage, capital V, then we may have such instant that Vc will be equal to V, and when our Vc will be equal to V, then we have the voltage across the capacitance will be equal to 0, so that this voltage across the switch will be equal to 0 because Vc equal to V, and at that condition we will get the V of VSW is equal to 1, that is the logic. So VSW is equal to 1 when the Vc is equal to V, or we can say when the voltage across the thyristor switch is 0. Now for the first, if we give the on request to the TSC branch, so when there we will receive the on request, that is our logic will be on is equal to 1, and this condition, our first condition, that voltage across switch should be 0, that is VSW is equal to 1, then we will give the triggering pulse to this thyristor and it will switch on the TSC branches. Or in second condition we may get the Vc greater than supply voltage, peak supply voltage. So when this Vc residual voltage across the capacitor is greater than the supply voltage, then we should ensure that the voltage across this switch should be minimum. So when this voltage across switch will be minimum, that is when both supply voltage and the voltage residual voltage across the capacitor are in the same quadrant, or we can say both either are positive or both should be negative, then this voltage will be minimum. So second condition arises that we should get the on request and Pt should be equal to 1. So when this Pt synchronization switch should be 1 and V pole should be equal to 1. So what is V pole? That is the polarity should be same. So V pole should be equal to 1 when the sign of supply voltage equal to sign of Vc, residual voltage of the capacitor, that is when the supply voltage and Vc either should be positive or both should be negative, then we will get this V pole is equal to 1, and we will get Pt is equal to 1 when we will get the V supply voltage is equal to at its peak voltage. So when supply voltage will be at its peak maximum voltage, then we will get the minimum voltage at this switch. So these are the two conditions. So if you have on request, then you will require the synchronization with the Pt and V pole is equal to 1. So these two conditions should be satisfied along with the on request. And in second case, you will give a triggering pulse when your VSW, voltage across the switch, is equal to 0, that is the condition VSW is equal to 1, and you should also give the on request to turn on the TSC branch. Now we will see the operating VI characteristics of the TSC TCR type of